Hi, my name is Olivia, and I will be discussing Team 22's experiment for determining the optimal expansion valve for the chiller.
In this experiment, the three main objectives are to determine the chiller's coefficient of performance and seasonal energy efficiency ratio as a function of water temperature. We will not only determine this for one, but two expansion valves, the throttle and orifice. The second objective is to calculate tonnage of cooling as a function of water flow rate. The third objective will be to plot the pressure enthalpy diagram for the chiller. To accomplish these objectives, the flow rate of inlet water will be changed to achieve the desired results. The chiller is a basic refrigeration cycle. The first step of the refrigeration cycle is the expansion valve. For the chiller, there are two expansion valves to choose from, highlighted in orange. The expansion valves exhibit the Joule-Thomson effect. When a fluid expands through a throttling device such as a valve, the pressure will drop as well as the temperature of the fluid. The now colder refrigerant will flow into the evaporator coils, shown in the image to the right in gray. The refrigerant will flow countercurrent in the opposite direction to the water through the coils. By doing this, heat transfer will occur as the refrigerant takes heat from the water. The third step of the cycle is the compressor, highlighted in yellow. The refrigerant is now a hot, low-pressure vapor. It will pass through the compressor, where the pressure is increased to allow refrigerant flow to the condenser. Before starting the cycle over again, the refrigerant will pass through the condenser boxed in blue. The condenser acts to cool the refrigerant by a fan circulating cool air.
The first step for calculations is to determine the heat transferred in the evaporator coils. Since it is more documented, water will be used to calculate the heat. This heat can be used to calculate efficiencies of the refrigeration cycle. The coefficient of performance, or COP, measures the performance of the cycle and is the ratio of heat divided by power input. The seasonal energy efficiency ratio is similar to the COP, except it measures the performance of an air conditioning unit during a cooling season. The total tonnage can be calculated by simple unit conversion of heat. According to Engineering Toolbox, a ton is the amount of heat removed by an air conditioning system that would melt 1 ton of ice in 24 hours.
While we never come into direct contact with R22 or Freon during the experiment, it can pose a serious hazard to health and the environment. R22 also contains chlorine, which is known to react with ozone in the atmosphere. If R22 leaks from the chiller, or a typical air conditioning unit, it can cause further depletion of the ozone layer, as well as other serious environmental concerns such as acid rain. These hazards are why at the beginning of 2020, the United States can no longer make or import Freon. This can cause issues for maintenance of the unit as the refrigerant can no longer be made here legally. Firsthand, we have already started to see the effects of this playing out. On the first day of lab, we were unaware that we were running low on Freon, but luckily more was found for day 2. It can be seen from the images that flow becomes consistent on day 2 and the bubbles and turbulence have disappeared.
A throttling device can control the amount of refrigerant going to the evaporator by looking at the evaporator temperature as well as pressure. As seen in the internal diagram, a spring is constantly pushing up on the diaphragm. The bulb pressure will push the diaphragm down if the temperature gets too hot, while the evaporator pressure will push the diaphragm up if the pressure gets too high.
An orifice tube contains a small restriction in the pipe that restricts refrigerant flow. This restriction allows the refrigerant to expand and induces a pressure drop of the fluid. Unlike the throttle valve, there is no moving parts at play, so failure modes are less common.
During the experiment, pressure was recorded for each run and the enthalpy was calculated using Aspen Properties database. The R22 in this process starts as a saturated liquid. For the first part of our cycle, R22 goes through an expansion valve. This expansion valve will drop the pressure of the refrigerant in a nearly isenthalpic process. R22 will now become a saturated liquid vapor mix. This liquid vapor mixture will absorb heat from the hot water in the evaporator coils. The temperature of the refrigerant will increase while the pressure will remain constant, leading to a nearly saturated vapor as it exits the evaporator. Since the pressure is so low, in order to maintain flow, a compressor will increase the pressure up to 200 psi. The compression of a vapor is a nearly isentropic process, so the curve will follow the dotted blue constant entropy lines. The R22 vapors will now be superheated. The heat from the refrigerant will leave in the condenser. This brings the R22 vapor to a saturated liquid, then the cycle will repeat again. For COP, the highest value is the most desirable because more heat is removed than energy put into the system. As the temperature difference decreased, meaning less heat was transferred from the water to the refrigerant, the coefficient of performance tended to increase. The highest COP of 5.3 occurred at the smallest delta T of 3.4 Kelvin. This trend is not entirely intuitive. We would expect that the coefficient of performance would increase as the temperature difference increases. It actually does, but since the coefficient of performance cannot be mass normalized, the mass flow rate dominates the equation. The higher mass flow rate will increase the value of Q, despite the delta T being smaller. The same trend can be seen with the chiller's seasonal energy efficiency rating. For air conditioners, the higher SEER value is better because it leads to greater cost savings. The highest SEER value recorded for the orifice valve was 18 at the smallest delta T of 3.4 Kelvin. According to the U.S. Department of Energy, 14 is the minimum efficiency standard for the southeast region of the United States.
The maximum COP for the throttle valve was only 3.9 compared to the orifice COP of 5.3. The same negative correlation occurs for the throttle valve that was seen with the orifice. As the delta T gets smaller, we have a greater COP. This is again because the mass flow rate dominates the equation. SEER values reach a maximum of only 13.3 compared to 18 for the orifice. This rating would not be acceptable for an air conditioning unit in the South, as none of the SEER values reach 14. While the throttle valve was less efficient than the orifice, the error tended to be much lower, as seen by the barely visible standard deviation bars. To reach an outlet temperature of 15 degrees Celsius for water, the water flow rate had to be on average 1.5 gallons per minute for the throttle and 1.7 gallons per minute for the orifice. This higher flow rate raised the heat to 5,232 watts, leaving the water, giving a larger tonnage of cooling. A higher tonnage means that the orifice has a greater cooling capacity, which is more desirable. This falls in line with our previous data that the orifice valve had greater efficiency than the throttle.
From the data, we can conclude that the orifice valve is the more efficient valve for the chiller, despite it having the highest error. From the manufacturer datasheet, we found most of the experimental uncertainty for the instruments used. From there, we discovered that thermocouples are meant to be submerged in a fluid and not for direct solid contact. This is a potential source of error for our temperature readings. We calculated the uncertainty correction for the thermocouples to be as high as plus or minus 23%. Ideally, if we could conduct day 3 of experimentation, we would focus on getting more data points to pinpoint with more certainty where the error is coming from.